Hey guys, this is Einar. I hope that you're doing great today, and welcome to this tutorial where we are going to conduct a two-sided hypothesis test using the Z distribution for the difference between two sample means. And now, before I even begin, I can say that I could say a lot about this test variable formula. It looks more difficult than it is, so relax. It's not as hard as it looks, but this is basically the test variable that we're going to be using, and I'm going to go through the different parts of this formula before we begin, so you have some idea of what's happening. But you read up on the course literature if you're really curious about the intricate parts of this. It's actually really interesting, so I recommend you do that. So let's take a look at the formula. What do we have here? Well, we're testing the difference between two sample means, right? So they have to be part of the formula somehow. And that's this part of the formula. Okay, so this is our first sample mean, and that's why there's a 1 there. There's an index showing that this is our first sample, and this is our second sample. That's why there's a 2 there. And because we're always testing the null hypothesis, we're saying that this difference is going to be equal to 0. That's what we're assuming. Furthermore, consider the fact that, these aren't population means, these are sample means. So we haven't asked everyone in this first population, and we haven't asked everyone in the second population, so we have uncertainty that we have to take into account. Now, in the case of the first sample, this is the uncertainty that we're going to take into account there. And as in earlier tutorials, it consists of two parts, okay? So it's partly the variation around the mean. How different are the people in our sample? That is going to affect how certain we can be of our estimate or our guess of the characteristic that we're measuring. And how many people have we asked? That's also going to make a difference, right? If I only ask one person about something, I can't be as sure as if I asked 1,000 people. So we're taking the sample size and the variation into account. And we're doing this for the first sample, right? That's why there are ones there. And we're also doing this for the second sample. So this is the variation around the second sample mean, and this is the number of people we have in our second sample. So that's actually pretty similar to what we've been doing in the earlier tutorials. This part of the formula you can actually just ignore for now if you're not really curious, but what it represents is this is the true population mean for the first population. That's why there's a 1 there. And that's what we're drawing a sample from. So this is the true value of what we're estimating using the mean in this sample. And this is the true mean in the population that the second sample is being drawn from, right? So this is the true mean for the other mean that we're comparing to. And we're assuming that these are going to be equal to 0 as well, because we're testing a null hypothesis. Now, the further away this z is from 0, the more likely it is that we actually have a real difference that is not just due to variation. If you take a quick look at our normal distribution here that we're using to test, we can see that the 0 is here. So when this is z, this is the z axis. So when there is no difference between the means, we're going to get a z value that is 0, and we'll end up right here. And if this is the case, if this was the case hypothetically, then most of our samples would actually end up somewhere around 0. That's why the curve is at its peak right here. And then due to just random variation, because we're not asking everyone, we're always going to get a small difference anyway. And the larger this difference is, the less likely it is that it happens. So if we conducted this over and over and over and over again, most of our samples would end up here around 0, and a few, very few, would end up here in the tails. Now, the important part here is that if we actually get a difference that is kind of large, that ends up here in one of these tails, it is becoming less and less likely that this is just due to random variation. It seems then that in fact there is a difference. This idea that our z is going to equal to 0 seems to be untrue, and that's basically what a hypothesis test is. We're going to take a look at our samples. We have our tango dancers here, and we have our Lindy Hoppers here. So what we're testing the difference for is the number of Facebook friends that tango dancers have and Lindy Hop dancers have. And it's kind of fun because I actually collected this for real, so this is a real data set. Yay! And basically, these are the number of friends that tango dancers have. I'm pretty excited about this actually. And this is the number of Facebook friends that Lindy Hoppers have. And we're going to test if there is a difference between them. If there is a difference, maybe their Lindy Hoppers and tango dancers are different somehow. So quick look at the formula again, what we need. Well, to begin with, we're going to need the sample sizes. It's always good to calculate that first to get an idea of what we're testing here. So first, we're going to count the number of tango dancers that we have asked. Or in other words, the number of tango dancers I looked up on Facebook and checked how many friends they had. 147. Okay. And for the second sample, I'm going to count them. Okay, so we have 50 Lindy Hoppers. And remember, if you're doing a study like this, these samples have to be randomly selected, okay? So just bear that in mind. Next, we're going to calculate our estimates. So we can actually start getting an indication if there is a difference now or not already. So I'm going to calculate average for my Tango dancers. So let's find out the average number of Facebook friends that Tango dancers have. And we find that they had 245 friends on Facebook on average. Okay, the Lindy Hoppers then, how many friends on Facebook do they have? We're gonna find out. They have 361 Facebook friends on average. So could we now say that, well, look at these numbers, huh? It seems like the Lindy Hoppers have more friends on Facebook than the Tango dancers have. Or can we be sure about this guess? Well, no, not really, because we haven't asked all the Tango dancers in the world, and we haven't asked all the Lindy Hoppers in the world how many friends they have on Facebook. We have asked, to be specific, 147 Tango dancers and 50 Lindy Hoppers. So there's uncertainty here that we need to take into account, you know, this part of the formula. We have this part of the uncertainty, we've calculated our sample sizes, but we're also going to need the variation within our samples, because that is also a measure of the uncertainty. So I'm going to calculate the variation using equal to var. I'm going to select my Tango dancers here. Close that parentheses, and it's equal to this number. For the Lindy Hoppers, I write equal to var. I'm going to calculate this for my Lindy Hoppers. So this is the variation that I'm calculating. Not the standard deviation, it's the variation. In some previous tutorials we have been using the standard deviation, just bear that in mind. But now we're using the variation, so we can see that we have the variation here for the Lindy Hoppers and we have the variation here for the Tango dancers. And there seems to be a lot more variation among the Tango dancers than among the Lindy Hoppers. You can see that. This number is a lot larger than this one. So we are actually, it seems like we may be more unsure of our guess here among the Tango dancers than the Lindy Hoppers. But then bear in mind too that we've asked more Tango dancers than Lindy Hoppers, so we don't know for sure, basically. But we have now everything we need to calculate our test variable, right? We have our estimates, we have the variations, and we have the sample sizes. So you see this formula isn't as complicated as it looks. We have all the different parts already. So let's start calculating it. We're equal to. We're going to take the difference between our sample means. So x1, well, that's the Tango dancers, minus the Lindy Hop dancers, divided by the square root, parentheses, and I'm going to take the variation in my first sample divided by my first sample size. Okay, the variation we have here for the Tango dancers, divided by how many Tango dancers we have asked. So this is the uncertainty we have in our first sample. We're going to add that to the uncertainty we have in our second sample. So that is going to be the variation among our Lindy Hoppers divided by how many Lindy Hoppers we have asked. And I close that parenthesis, and we have then our two parts of the formula for our test variable. So I hit enter, and we get a test variable of minus 2.49. Now notice, this is not 0, right? This is not equal to 0. If I just for fun set this to equal to 245, I would get something like 0. Then there would be no difference between the two means. But this is not true. This is what we found empirically. There is a difference, and the test variable becomes a number which is going to be tested. Is this number large enough to say that this difference is in fact not just due to random variation? In fact, in other words, is this number large enough, far away from 0, for us to be able to say that, well, it seems that it's pretty unlikely because it's out in a tail that this is just due to chance, so there is a real difference. We do this by calculating critical Z values, and you can look them up in tables. I've done this for us. In the case of a 99% confidence level, we have a critical Z value 2.58. So what we ask ourselves then is our test variable larger than, and I'm talking about larger in absolute terms now, because we're not saying anything about the direction. So I'm just saying, is this number larger than 2.58 plus or minus 2.58? And is it larger? No, it's not. If we take a quick look here at the formula, we see 2.58 it's pretty far out in the tail, but then again, we are using a pretty high confidence level. And our test variable minus 2.49. Well, if we move there along the x-axis, it's somewhere around, I suppose, somewhere around there. So it's not outside of our interval. It's too close to 0 for us to be able to say that there is a real difference. We're going to have to say that our null hypothesis is true. And the null hypothesis is that there is no difference between the sample means. Right. And that might seem like bad news, you know, but then again, a 99% confidence level is a very high confidence level. So what it means actually is that if I conducted my sampling procedure 100 times, I just did loads of samples. I asked like 100 samples of tango dancers and Lindy Hoppers, and I calculated the difference, and the difference was distributed normally. I would have a 1 in a 100 chance that, and I would get a critical Z value in one of my samples that was outside of the interval of minus 2.58 and plus 2.58. And basically that's what a confidence level means. If I, however, move down to 95% confidence, and this is pretty common in the social sciences, I have a critical value of 1.96, and then again, check this in the tables if you're curious about that. Is our test variable larger than 1.96? Yes, it is. In absolute terms, it is larger than 1.96. So what we're doing then is we're saying, okay, we couldn't be this sure. We have to include more uncertainty here in our tail and move all the way down here to 1.96. So we have 2.5% there and 2.5% in this tail. So plus 1.96 minus 1.96. And we're looking if our test variable of minus 2.49 is larger than that. Yes, it is. It's to the left of minus 1.96. It's out in the tail here. So at 95% confidence level, we can actually refute the null hypothesis and say that yes, there is a real difference in how many Facebook friends tango dancers and Lindy Hoppers have. So we're saying basically that if we conducted our sample 100 times, in 95 out of these 100 times, if there was no difference, we would get a critical Z value from each of our samples that was in between the interval minus 1.96 and plus 1.96, and that's not what we're getting. So we're saying that, well, there is a real difference, and the chance that there is not a real difference, that this is just a freak accident like to the chance, is basically 5 out of 100. So that's how you calculate an hypothesis test using this test variable formula for the difference between two sample means. I hope you have some fun with this. Try doing what I just did, and I change the difference manually and looking how the test variable changes and figuring out the relationship between this and the normal distribution. Have some fun with this. It became a really long tutorial, guys, but I know, but it had to be. Good luck with this, and I hope to see you in the next tutorial. Have a really great day. Bye-bye.